Well, good afternoon. It's a real pleasure to be here and an honor to be able to talk with you today. As Ali said, I'm going to talk about a new decision science for complex tools, the systems, a decade of enabling tools. And let me just start out with, there we go. You know, we face a number of very hard problems, and one of the topics of this conference is how can systems analysis, how can quantitative analysis best support these really hard problems. And one of the things I'm going to do in my talk is really put proper nouns on a lot of the themes I think that we've been talking about. And so the first one of these is this idea of wicked problems, which I think is a theme that cuts across a lot of the examples I just showed you and a lot of the discussions that we've been having. And so a wicked problem has various characteristics. They're not well bounded. They're framed differently by different people. Large uncertainties, nonlinear dynamics, not well understood, and this is important until you formulate the solution. And I think many of the problems that we've been discussing have these characteristics. So let me just lay out some of the characteristics of us in our world that tend to make these problems hard. On the left is a quick list of some of the many biases in human reasoning. I've attributed these to Kahneman, but they obviously come from a lot of different places. But people are overconfident, take actions inconsistent with their interests, avoid trade-offs, employ heuristics which maybe not work very well in the situation they're in. On the other side is this notion that heterogeneity and deep uncertainty are fundamental characteristics of our world, that people have diverse priorities and goals and worldviews, that there's really irreducible uncertainty in the consequences of our action. I'm taking this language from Amartya Sen's work trying to build a logic of ethical reasoning on a foundation of social choice theory. Which this is his book, The Idea of Justice, which I find fascinating. And, in some sense, we can regard what's on the left as bugs, which in human reasoning, which can be greatly enhanced by the use of decision support tools. And obviously, you can show this experimentally, that people do much better with tools than without. But on some hand, the things on the right are features that make the use of tools that may be designed for simple problems fail for wicked problems. The one in the middle is interesting. It's both a feature and a bug. So let me show you the bug aspect of it. And I decided to show this inspired by the wonderful talk we heard last night. But it turns, and this is from the work of Dan Kahan at Yale in cultural cognition. It turns out you can measure people's scientific intelligence, and then if you ask people scientific factual questions, it correlates really well with this measure. So if you ask them what gas makes up the majority of the Earth's atmosphere, the answers correlate very well with these measures of scientific intelligence. If you ask them a more fraught question, say one involved with climate change, the correlation largely goes away. But interestingly, if you divide it up by identity groups, people who self-associate with one another, share a worldview, the correlation comes back for one and it's anti-correlated for the other. And notice that the more educated you are, the more you know, the less you believe these statements, in part because you become very skilled at finding weaknesses in the arguments. But interestingly, if you then ask a question that's not related to your identity, not what do you believe, but what does the other guy believe, it turns out that people do. First, the correlation comes back, and in fact, the conservative Republicans do better than the liberal Democrats to some extent in knowing what the climate scientists believe. So this is the situation. This is the sort of, so just more education doesn't work here. So how do we put analytics into these sorts of problems? Two key ideas I want to talk about. I'm going to put this label decision support on a lot of the participatory processes that we've been talking about. This document down here is a U.S. National Research Council report, which tries to codify these ideas of decision support, looking across dozens of different policy areas. How does working with analytics and in participatory processes work? This is the definition, and there's some key elements of effective decision support, which we've heard a lot about in other talks. A recognition that the decision process is as important as the products. This co-production of knowledge between users and producers, institutional stability between those two groups so that you can build trust and understanding, and design for learning. One of the most important learning processes, in particular in the sort of work that I'm talking about here, has this name deliberation with analysis, and I sketch out the process here, but this is essentially the process of co-production of knowledge. And it's particularly important when people's expectations and their values are non-stationary, in that they change with interactions both with the data and in interactions with other people. Okay. The other important idea is this idea of exploratory modeling and using our models in different ways. And this comes originally from my former RAND colleague, Steve Bankus. But he distinguished between two types of models, exploratory and consolidative. Consolidative, what we're often used to, and what we use in engineering, often in science, they're consolidated, they pull together all the relevant information to a single package, which when we validate them can be used as a substitute for the real world, which is often a useful thing to do. So weather prediction is a consolidative model. There's another type of model, however, which is exploratory, which maps assumptions onto consequences without privileging one set of assumptions over the other. And you see this starts to link to the multiple worldviews that we heard previously. And what I'm going to argue is that the tooling that people often use exploratory models, but it's really a question of allocation of computational resources. Sort of the natural thing we often do is, oh, we've got more computational resources, we've got more time, let's make our model a better predictor, let's make it more consolidative. And the tools are now coming to the point where we can actually do an awful lot more with exploratory modeling, as I'm going to lay out, and I list some of the ones I'm going to talk about here. So actually, I would say a pretty significant community coming around these sorts of ideas, and I list key principles for decision support under conditions of deep uncertainty. This idea consists looking at a multiplicity of plausible futures, seeking robust as opposed to optimal strategies, often enabling robustness with adaptivity, and then using the computer to facilitate discourse among humans as opposed to a machine or a calculator that tells us the best thing to do. And actually, just last week, we had the third annual workshop of people who work in this style of decision-making under deep uncertainty. It was in Delft. This very much encourage people to Google this, look at the site, and hopefully join this group. It's actually some exciting stuff going on there. Okay, so I'm going to basically give a little tour here. I'm going to talk about work we've done over the last, and others over the last decade and a half, showing you some initial explorations, going to laying out some details, some of the tools, and then talking about current state-of-the-art next steps. And the first ones and the last ones are complex systems models. So we actually started doing this with models of complex systems because they had this characteristic of deep uncertainty. We've had a long run actually just using spreadsheets and hydrology models, which are they themselves not deeply uncertain, but are in deeply uncertain contexts. So I'm going to talk about work we've done there and then turn back to some recent work we've been using in these ideas in more complexity. So just a couple of quick, just going through these examples quickly. This is work we did about 15 years ago, using agent-based models to ask the question, what sort of mix of policy instruments do we want to use to help decarbonize the economy? And agent-based modeling was useful here because we thought that heterogeneity and social benefits that diffuse through the network were both important. We built a model, ran a huge number of cases. We filtered them to be consistent with history, but then they go off in this gigantic fan in the future because history doesn't constrain where we're going all that much, and so I show that there. And essentially, we went through a series of steps with that model that was sort of, we've systematized since then, but I think are fairly indicative. Looked at two strategies. We stress tested them over this large ensemble. We then had a giant database, which by hand in this case, we projected down into a low-dimensional space. And you get an answer here. Ask the question, what are the key drivers that differentiate you wanting to just use price instruments and price instruments plus things like renewable portfolio standards, more focused technology instruments? Turns out the two important things are the size of the climate impacts and the extent to which the world you're in deviates from what we called a classical world or the probability of a non-classical world, which in this case had to do with the heterogeneity, the networks, and the extent to which early adopters created social benefits, which they themselves didn't capture. And you got these if you're down in the lower corner, you ought to do just price instruments. If you're not, you're not. And then, which I think was a sort of very fun idea that my student had, which is while we spent the several months writing the paper, we launched a GA against the model space to look at many millions of combinations that we hadn't actually looked at to find counterexamples to the statement consistent with history and giving you a different order of policies. And after 2 or 3 months, the GA found a couple of cases, but they were not particularly credible or interesting. So let me now talk about, I'm sorry, and this is a template as a means for generating policy relevant results from these sorts of models. Let me talk a little bit about how to more systematize this and give you some current examples. So essentially, you know, the kernel of the argument is this, in that in conditions of less deep or more well-characterized uncertainty, we've got a beautiful set of tools where we first characterize, reach agreement on what the future may hold in terms of single joint probability distributions, well-characterized value functions. We can then rank decision options, and then we can do some sensitivity analysis. This works beautifully in many cases, but under conditions of deep uncertainty, it has various problems. It encourages you to underestimate the uncertainties. Competing analysis can lead to gridlock. And we often know a lot that can help us deal with surprise, which is not very predictive. Under these conditions, it's often useful to turn the analysis around and you use your analytics essentially to stress test alternative policies, to make high confidence statements about where they work and where they don't, and use that as a means to reach consensus on ways to hedge against them. It's useful, this is a chart that I have appropriated from the meeting last week from Casey Helgeson at LSE, who did a broad literature review of various ways to look at uncertainty. But essentially, if we think of decision structuring and choice tasks as part of what we're doing in decision support, forward analysis often is very much focused on making rational choices as looking for inconsistencies in people's reasoning and coming up with a rational ordering. The sort of analysis I'm talking about is much more interested in decision framing, helping people come up with an agreed framing or to see each other's framing in a way that then they can make the choices themselves, essentially giving them Pareto surfaces, low-dimensional Pareto surfaces so they can make their own choices, but having a systematic way for giving them the low-dimensional surfaces that they ought to be working with. Okay, so robust decision-making is one way that we've structured this, and it has a series of steps. And the point is just in each of these steps, there are these beautiful emerging tools that allow you to implement them. I was asked to focus on this one, scenario discovery. So let me just give you a quick example, a quick tour of the scenario literature, which is scenarios are fabulous for addressing cognitive barriers. And so I've got a couple here. I'll just focus on the first one, which is this cat has great expert experience in dealing with birds, but he could probably benefit from a scenario analysis because this encounter is not going to work out like the others. But scenarios can be very ineffective in some political contexts. They can be ambiguous, they can be seen as biased, and so forth. And so let me give you an example. And so what one can do is have the scenarios emerge from the analysis. So you run these large databases of simulation model runs. You use classification algorithms on them to answer the question systematically, what is the best low-dimensional projection of this large database that distinguishes the futures and where the policy works from where it doesn't, or where you choose A versus B. And the resulting scenarios can often provide effective decision support. So let me linger for a second on this example. This comes from a RAND study of terrorism insurance. Essentially, right after 9/11, the commercial insurance industry realized that they had been insuring us stuff like the loss of the World Trade Center, so they immediately dropped their policies. The federal government put in free reinsurance for the insurers, and they reinstituted their policies, and then the law came up for reauthorization some years later, and the question was whether to reauthorize it. We went through an analysis just like I showed you, came up, it was multi-objective, but I'm showing you one objective here, and the question, does this reauthorizing this law save the taxpayer money or not? And it turns out that there's many factors being debated in the discussion, but it turns out that two are most important. Is the probability of a large attack. This means that what the reinsurance industry thinks the attack is is right. We go over 3 orders of magnitude here, and this is what future Congresses do with the uninsured, how much they compensate them. If you're in here, it saves you money. If you're outside, it doesn't. And just a few interesting things to say about this scenario. First off, it proved reasonably effective in the debate. It was quoted on the floor of the Senate by a proponent. A major national newspaper didn't like this analysis, but the worst they could say about it was insidious, which we took as a compliment. Interestingly, it was different. It was consistent with the U.S. government official forecasts used for budget scoring, which were down here, but showed you that there were a wide range of other possibilities. And it mixed uncertainty with probability and state space, so we're dealing with both. And then interestingly, it mixed external and internal drivers. This is external, this is internal, which I think is actually important. There's been some discussion here about sort of the influence of neoliberal ideas and politics, but the notion that you can separate the attributes of the actor from the attributes of the external environment is sort of the classic, perfect market idea where one agent can't affect the external environment. And much of the scenario literature comes out of people who are working in that environment, at least with those assumptions. It doesn't make any sense at all for a government which is trying to fundamentally reshape the external environment. And we often find that when you do this sort of emergent scenario, that it's a strong mix of internal factors and external factors, which I think is important in thinking about proper use of scenarios. Let me quickly take you to two current state-of-the-art. This one is, again, using complicated models, but not complex. This is work we did for the U.S. Bureau of Reclamation, helping them manage the Colorado Basin, which serves about 40 million people in the U.S. The challenge simply is the river was allocated 100 years ago at the high water mark for millennium, so the supply has gone down, the demand has gone up, they've crossed. The stakeholders need to figure out what to do. The writer, American writer Mark Twain said that whiskey's for drinking, water's for fighting, so this is a pretty contentious group, 7 states, a variety of big cities. We eventually helped them reach consensus on a description of the challenges and some ways forward. This study was released by the U.S. Secretary of the Interior a couple of years ago. Just to take you through it real quickly, we worked in this deliberation with analysis process that I showed you, 2 years of workshops. In the analysis, we would stress test strategies over 24,000 alternative paths, identify scenarios as I was showing you, and suggest portfolios of responses, robust over those. Just real quick, we were using the large-scale hydrologic simulation that Reclamation has used for 20 years, so using old models in new ways. And just to give you a quick tour of the results, and these are actually pictures that come from a dissertation that was subsequent to the actual study, but it turns out that over all of those uncertainties, over all of the things you might worry about, it turns out that the two things that influence whether or not current management plans on the Colorado River work is the 50-year average flow driven by climate change and the driest 8-year period, which is not too surprising since that's about the storage on the river. You end up with these 4 categories. Up here, business as usual works. Down here, nothing you can do work. And here is a series where whether or not you meet your 26 different objectives matters a lot about what you put in when. And you can lay these out in adaptive paths and drive people to consensus on what near-term actions they should take, what they ought to monitor, and what they ought to think, and what they might do in response to different monitoring. Just very quickly, let me just go through this new agent-based modeling work, which is addresses this question of the gap between climate action and aspiration. And as we all know, it's pretty hard at this point to reach the 2-degree target, and none of the policies on the agenda do that. This is some work by Celine Gavarich and Stefan Holgott, which basically shows you the rate of decarbonization you need to hit different targets. And the point is, here are roughly where the pledges are. This is the fastest any country has ever gone, which is France when it put in its nuclear power program. And so, this is a major challenge. In addition, just quickly, is that many of the analyses focus on policies that people actually can't implement because they're long-term targets, they're long-term reduction paths, and that's not under the power. Policymakers recognize this. This is a couple of lines from President Obama's recent interview with Rolling Stone about what he's thinking about in terms of the Paris talks. And he says, well, I'm less concerned about the precise targets. I'm more interested in creating momentum. Can we say anything more systematic about momentum? Well, the political scientists actually think about this, and they ask the question, why do some policy reforms persist over decades while others do not? The model here is sort of the window of opportunity. I can put in place some legislation. Is it going to last decades or not? Clearly, current policy has to last decades. And so here are some, at least in the US context, policies which persisted over time. Here's some that don't. What's the difference? Well, these all have constituencies that were created by the policy. This one doesn't. So can we say something about using this formulation about greenhouse gas policy? There's a paper we just did in Global Environmental Change. So we put together an agent-based model that drew on 3 literatures, this political science literature on policy persistence. There's some game theoretic models from the trade literature which ask, how do tariffs go up or down as a negotiated settlement between the government, which is looking for the social optimum, and firms, which are competing for different policy outcomes? So we changed tariffs to carbon taxes, and then an agent-based evolutionary economic formalisms, which look at the co-evolution of expectations, technologies, and then back to expectations. We looked at a wide range of different policy architectures, these basically taxes, cap and trades, and different ways you can exclude people from the taxes and different ways you can handle the revenue. The notion, these are all things that one could do today if you had a legislative majority, even if you lose it later on. A lot of futures, 2.7 million runs. We've got a big database. We search for useful conclusions, and we actually find some. So first off, excluding incumbents, essentially grandfathering, makes no difference. There are a lot of cases where, in fact, putting in revenue transfers, essentially revenues flow from high emitters to low emitters, creates large incentives to form coalitions for high carbon price. So it can actually give you very significant increase in the carbon price over decades. The key drivers of that has to do with the elasticity of demand, because that opens up a space to capture market share even if the total market goes down. The potential for R&D to generate low carbon intensity, and various combinations of government preferences. And interestingly, a key variable seems to be what agency you give in the government to administer the carbon price, because that affects how the firms lobby and interact with it. And this is just to remind you that there's a big model underneath this, and this is for one run how the coalitions form. Oh, I'm sorry, that got messed up. That's supposed to be the negotiated carbon price over time. But basically, there's 2.7 million of those runs, and these are a low-dimensional summary of what you get out of them. Okay, so let me talk just for a minute or two about next steps. Here's our little RDM loop here. And so I was asked to talk about this part down here, which is the vulnerability analysis. There's also the new strategy, the new option generation, and trade-off analysis. There was a question in the last talk about Anna's talk about this participatory process. She said, well, what about complicated, robust options that the stakeholders don't think of? Well, it turns out that there are a lot of tools to do that. And the Colorado Basin one I showed you was one, the Louisiana Coastal Master Plan. The report came out a couple of years ago. These are all highly complex stakeholder deliberation with analysis. This one was, again, about 2 years of work, an immensely complicated system where there's a budget constraint, and if I build a levee in front of my parish and wetlands in front of yours, it affects the flow on the third parish, and none of that is very obvious. So using models with a high level of multi-objective, robust optimization to essentially give the stakeholders low-dimensional Pareto surfaces that reflect their key differences in worldviews, you can actually move them towards much more robust solutions than they would have otherwise found. This plan passed the Louisiana legislature unanimously, which is quite a feat, I think. And this is just some recent work by one of my colleagues, Pat Reed, and his group, where they've got a very powerful set of genetic algorithms in a very complicated system here. This is the coupled water systems around Raleigh-Durham in North Carolina. So you have 4 jurisdictions, you have multiple scenarios with deep uncertainty, and they help them move towards very complicated mutual robust strategies which have to do with both the water management system and then the financial instruments they use to manage risk, solutions that they would have never found on their own, but never would have got to if they just had the model loan out in this participatory process. So just to end, fortunately, systems analysis can prove useful for wicked problems, but we really need to pay as much, if not more, attention to the process of using models as to the models themselves. I think a good process can survive a bad model, but a bad process isn't helped by a good model. We now have the computational tools, these scenario discovery, these multi-objective optimization, to really take these ideas which have been floating around for a while and put them into actual practice. And I think these things are going to be even more important as we grapple with transformative policies and thinking about the role of institutions, both as constraints part of the model and as part of our policy instruments. So, thank you.